today is to first of all talk about log property decomposition. And second of all, to talk about logarithmic differentiation. The first is old news. It's stuff that you have already known how to do, but we're putting a new name to it. The second is going to be an application of that so that we can get derivatives of functions that have variable exponents or that are complicated products of functions. So let's get to it. First thing that I'd like for you to do in your notes, you can take this as a non-counting Quizlet. I'd like for you to give me the 3 log properties. Go.
Oh, from yesterday? Wait, log or ln? Log, yeah.
Just write them in terms of ln. Because for our purposes, ln is the most important log.
But they have the same property.
They have the same properties, that's right.
How you do that?
Okay. 3 log properties. Give me the product property, Gemma.
Log A times B is equal to log A plus log B.
There you go. Quotient property, Brian.
ln of A divided by B is equal to ln A minus ln.
Yep. And the power property, Sean.
ln to the A in parentheses to the B equals, yeah, something like that. Oh yeah,
That's probably what you wrote. We're going to pronounce this ln of A to the B.
Oh yeah, I might have done it wrong there. Unless it equals ln A plus B. No? No, yeah.
Yeah.
If B times
Yeah. So Sean, you had these 2, but then not that one?
Yeah.
Is that correct? Yep. So let's get this one right. The power property is that the log of a power is power times the log. Now, it turns out that working mathematicians love these properties. And the reason for that is that they allow us to take the 3 operations of multiplication, division, and exponents and simplify them to addition, subtraction, and multiplication. And in fact, that is the reason that logs were invented to begin with. John Napier created an entire table of logarithms by hand so that people everywhere could take a multiplication problem and use a log table to solve it simply by adding. To take an exponent problem and solve it using a log table by simply multiplying. And eventually those log tables got packaged into a cute little device that you may have heard of, your parents certainly have heard of, and they might have used, and your grandparents certainly used, called a slide rule. Have you heard of the slide rule before?
I guess my dad talked about it like one time.
Your dad taught, right, so everybody used to walk around with their slide rules in their pocket, and they were the BC, before calculator, version of the calculator. And the idea behind the slide rule is that you can quickly multiply numbers together by using the slide on here to essentially add in a logarithmic scale. So you would slide out your first number and then match it up with your second number, and the product would magically appear at the right interval. And it was done by setting it up with a logarithmic scale, so that by adding the logs, you were essentially multiplying numbers. Slide rules went out of fashion really just before I started like elementary school. electronic calculators were just happening when I was in elementary, middle, and high school. And now, of course, they have vast housing towers and all of that. So we're going to use these log properties now to simplify our lives in this way. Let's consider, first of all, just the algebra by doing log property decompositions of some different expressions. Now, what I mean by a log property decomposition is that I'm going to take the log of a complicated expression, products, quotients, powers, and I'm going to use the log properties to break it up into the sums of simpler logs. For example, let's consider this expression, the log of x squared times x quantity x plus 2. We take a look at that, we see that's a complicated expression that we're taking the log of, and it is a product of x squared and x plus 2, and x squared itself is a power of x, right? So this is a prime candidate for decomposing using the log properties. I'm going to look at this and identify x squared as a and x plus 2 as b. And I'm going to use my first property, the product property, to break it down as natural log of x squared plus natural log of x plus 2. And then I'm going to come back and look at that first term, and I'm going to recognize that I have the log of a power. It's in the form a to the b, the log of a to the b, and so I'm going to rewrite that as b times log a. How are we doing? Does this make sense to everybody? Now, you might very well ask, why would you want to do this? And I'm going to answer that question in just a minute. But does everybody see that we can do it? Click.
Is the AB just the rule you're using?
Yes, I'm identifying. Here I've got the log. If I were to write it in full, this would be my first rule. And then this guy right here so just this term would be how I'm getting from there to using power. Yes, ma'am.
In order to do this kind of thing, both of them would have to be the same base, right?
So the base is always
Yeah.
packaged into the
But if
log.
it was
Yeah.
like ln times log, you couldn't do this because they're two different bases.
Hey, that's a great question. If I am confronted with a log of any other base and I have the least trouble with it, then what I do is to apply my change of base formula. So for example, if I have something like this, then I would rewrite this as ln x times ln x over ln 2 using my change of base, and now I don't have to worry about it.
Okay.
You do this so you can write it easily?
Yeah, you can differentiate it easier. Yeah, that's right. Let's, in fact, in light of that, let's take a look at a couple of those homework problems. In one of your homework problems, you had y equals ln of 10 over x, and they wanted you to find dy dx. And I saw at least one student who was doing this by doing the log, the log rule here. And so this particular student did 1 over 10 over x times the derivative of the inside. All accurate, but working much harder than you need to. Watch what happens if I pull off a log property decomposition first. If I first take y, leaving the calculus alone, and I simply decompose this as ln 10 minus ln x using my quotient property. Now all of a sudden y prime is equal to the derivative with respect to x of ln 10 minus ln x, which is 0 minus 1 over x, and I am done. No chain rule, no quotient rule. Love it. Love it, love it, love
Which
it.
one was this? What number?
I don't remember.
That was the last one.
How do you know that?
ln 10 is 0.
Careful. I did not say ln 10 was 0. I said the derivative of ln 10 was 0.
That's fine.
Because ln 10 is a number that does not change. It is a constant.
So the other way's not wrong, it's just more work than.
A lot more work, a lot more error prone.
What else? I got it. I don't know, did you? You make it seem so easy.
Good. I'm glad it seems easy to you because I want it to be easy to you.
But then,
And the trick, the magic is found in the log property decomposition. And magic of that is simply know your three numbers. So let's do several of these, and then that'll give us some time for logarithmic differentiation. How about, in fact, let's pull some homework problems. Pick one. Yeah.
Number 24.
3 sets.
let's see. Y equals 1 over log 2 x.
Okay. So here, if I pull off a little bit of the change of base, then division is multiplying by the reciprocal. So what I get is ln2 over lnx. So far, for y.
Oh,
I have just changed y.
I thought that was oh.
So one of the things you want to be careful about is you want to do the algebra stuff, labeling that clearly as y. Now we do y prime. Now, unfortunately, here's where you want to be careful. I don't have a log property that really lets me do anything further with this algebraically. So I'm going to have to use quotient rule for this. I don't like it, but I'm sorry. That's okay. Low D high. Derivative of log 2 is 0. Yeah.
How did you know that log 2x was that? Yeah.
Ah, that's our change of base formula that we talked about yesterday. And by the way, did you guys discover last night I put a video up from period 6?
Oh,
it has a clearer explanation of the change of base formula. If you're confused about that, you might want to check it out. So, quotient rule. Low D high, less high, D low. All over denominator squared. And this gives us now a term that goes to 0 minus ln2. Watch how I handle the complex fraction. On the rewrite, division is multiplying by the reciprocal. So that I get negative ln2 over x and x. That one did not profit a whole lot by doing log properties. I mean, I got a little bit of leverage by doing change of base, but I wasn't able, because it was not the log of a quotient. Instead of quotient logs. I wasn't able to do a whole lot of log properties.
But the AP test do something like this?
Oh yes.
Oh.
They expect students to be able to do log properties and decomposition. Let me take a look at, how about number 17. Okay. In number 17, we have to find dy dx. And so before I embark on doing a derivative, first I want to consider, can I do a log property decomposition here? I can. And what do I get? Yes, sir.
I have a quick question about the last thing.
Yes.
It's just, we did low D high over.
Yes, quotient rule. ln1 minus ln x. Hey, that's one of our special values. What is ln of 1?
1 over 1.
No.
0.
Oh, 0.
So that before I ever get started on differentiation, no calculus done yet, I use my log properties to decompose this to a simpler form. We look at this, and it's pretty easy to see. We would much rather take the derivative of negative ln x than the derivative of ln of ln x. Notice also that if you're clever, you can get to this same decomposition a different way. Because this is also equal to the natural log of x to the minus 1 power. And using my power rule, I can rewrite that as negative 1 times natural log of x, which agrees with what we have here. So log properties often can get to the same point by different routes, as long as you're doing the log properties correctly. So now, having done this, we are ready to take a derivative. And we get y prime equals negative 1 over x. We're done. Isn't that so much simpler? You can practically do it in your head. Questions? Let's do one more. It's a good problem, but it's not a great example when I'm talking about some of the tasks. How about number 22? Okay. First of all, how am I going to handle the log 5 business?
I just turned it into a natural log, so I did ln square root of x, or x to 1/2 power over ln 5.
That's it. Oh, good. So we're going to first of all handle the log base 5 by changing its base. Please, please label carefully. I haven't done any y primage yet. No differentiation. I'm just rewriting y with the log properties. Now, does anybody see any further log property decomposition that can have happen before I get started? Square root is not negative 1 exponent. What exponent is the square root? The 1/2. Yes. Okay. And so now what? Not ready for a derivative yet because I can still use some log properties now. Okay, Christine is experiencing something that students will experience, which is their log properties fail them because they haven't yet internalized those forms.
Oh my.
Yep. So you need to, one of your goals for this weekend is to make sure that you can do the forms like that. Product of property, ln AB, quotient property, ln A over B, and here we have ln of A to the B half is equal to what? Help her out. Is equal to what?
1/2, that's all.
Exactly. Is equal to B times ln A. So the key to making this magic work is that you know your three forms hold. Because once you know the forms, then you will recognize those patterns when you see them. And you can do them with or without the parentheses. It doesn't change the meaning of it. If I know the form, then I can look at this and say, oh, there's my A, there's my B, and that's what I get. But if you think about it in terms of I do this and then I do that, you won't always see it. So knowing these forms is really the key to being able to see it and understand it. Does that make sense? So if you're one of those people that tends to do math by first I do this and then I do that, please learn the forms. Okay? Yes?
If it's okay with you, can we go over number 25?
Possibly. Now we're finally ready for a derivative, having done all of our decomposition. And the beauty of this is that I have a number of constant multiples. What are they? What are my constants? It's really 1 over ln5, right? Yep. And what else do I have as a constant? 1/2. So I'm going to bring the 1 over 2 and the 1 over ln5 to the outside, and the only thing I have left is the derivative of natural log x. And I can do that any day.
Wait,
1/2 is a constant. 1 over ln5 is a constant.
You can do it both. Can you do it both ways? Is that possible?
You mean, can I bring up two constants at once?
No, like say you don't even bring them out and you just do it for high, low, or
Yeah, you can.
Okay, but that's just
A lot. It is recommended practice. Anytime. In fact, if you do it with quotient rule, although I will not mark it wrong because it's correct, obviously, I'm still going to give you a little notation there. Do it the other way.
okay.
It's so much easier.
You pull it out and then
And we're done.
how did you want to read one?
that's right.
I would,
From here to here.
yeah, we're the one that's like,
Notice where the ln5 is located. It's located in the denominator of my fraction. So what am I multiplying by here? 1 over ln5.
You times the 2 to the 5?
What's that?
You times the 2 to the 5?
No, I didn't. I wrote it as 2 ln5.
Because in the book for 21,
They have ln25?
no, for 21, they had 2 divided by x out of 4. And you check the answer, they like simplify
Oh,
it.
yes. Okay. So, book answers will sometimes do the opposite of this. They will do logarithmic recomposition. So that's also possible.
What?
So, for example, if I have, for example, ln of x plus ln of x plus 1, and there's my answer, and I'm real proud of it. And I look in the back, and what I see is ln of x squared plus x. And I go, oh, I missed it. Wait a second, maybe I didn't. Let me recompose these using my product property. Bring my product property, ln of x is ln of x plus 1, is ln of x times x plus 1, which is x squared plus x. So sometimes we will go in reverse and take those log properties and put them all back together. We would do that to pretty up our answer. That's really the only reason we do it. Now let's take the example that you were talking about. 2 over ln of 4. I really wish they had not done this problem, because it looks like what they did was they just canceled out the two factors of 2. That's not what they did. What they did instead was they took 4 and they wrote that as 2 squared. And because it is 2 squared, it is therefore also 2 ln 2.
Oh,
And there's where your factors of 2 cancel. So it's just an unfortunate accident that 2 squared is also the same as 2 times 2.
okay.
Yep. If I were to do some logarithmic recomposition on this problem right here, I would take this 2 and this 5 right here, 2 ln 5, and I would write it as the ln of 5 squared. Just to pretty it up.
Do you have to do that?
No.
So, so you, math.
Yep. Devon, did you figure out your quotient question?
oh, yeah, I see what you mean.
Okay, good. All right, now let's actually leverage this technique of logarithmic decomposition to find the derivatives of functions that have variable exponents. this is beautiful math. Love this. I want to consider the function y equals x to the x. Very, very interesting function. And it is very, very interesting. First of all, it's interesting in the world of math because it grows really fast. F of 1 is 1, F of 2 is 4, F of 3 is 27, F of 4 is 256, and goodbye. It grows really, really fast. It grows faster than an exponential. It's sometimes called a super exponential. So I want you to observe that this is not a power. It's not in the form x to the n. And it's also not an exponential in the form b to the x. Instead, it's its own thing. So if I wanted to take the derivative, I would not be able to use the power rule, and I would not be able to use the exponential property either. What in the world could I do? Well, I could monkey around with the limit definition, but instead I'm going to do something very clever. I'm going to use logs to turn that tricky exponent into a multiplication problem. So my plan for y prime is to use logs to decompose, differentiate, and then solve. Use logs to decompose, differentiate, and then solve. And it works like this. I'm going to start with the equation y equals x to the x. And before I ever take a derivative, although I want a derivative, before I ever take a derivative, I'm going to take the log of both sides. This is the clever move that is going to turn my exponent problem into a multiplication problem. Because as soon as I take the log of the left right-hand side, I see, aha, power rule. The natural log of x to the x is the same as what?
X.
Times ln x.
I thought you had it.
And so here I have used logs to decompose a situation into a simpler situation. This was a brilliant move, taking the log of both sides. And what inspired me was the fact that I had that exponent sitting there. Okay? Now that I have decomposed it, I'm ready for a derivative with respect to x on both sides. Now on the left-hand side, keep in mind this is the natural log of y, so we're going to see what we've seen a whole lot of, the derivative of the outside times the derivative of the inside, 1 over y times dy dx. On the other side, I've got a product, so product rule is in order. First times the derivative of the second, plus the second times the derivative of the first. And at this point, you guys are experienced enough with the product rule that you probably don't need to write the intermediate step, unless it's really complicated. Now let's clean up the right-hand side here. What's my first term going to simplify as? 1. And the second term is ln x. Now, obey that equal sign. What is that equal to? It is equal to 1 over y dy dx. So therefore, if I'm looking for dy dx, dy dx is equal to y times 1 plus ln x. But now we see a theme that we've had a lot of before. I need to express this in terms of x. What is y? Go all the way back. Y is x to the x. So let's put that y back where it came from. And we get our really interesting derivative, which is x to the x times 1 plus ln x. Sean, question.
Oh, no, I understand.
The derivative.
Hey, actually, when you move 1 over y to the other side,
I didn't.
You did, wait, then,
Oh, you mean when I multiply both sides by y?
yes.
Ah, yes.
How did you get that? Oh, because y equals. Okay, cool.
Exactly so. Exactly it.
You know,
So let's do another one.
No.
The function x to the x is interesting and actually useful in areas like computer science. This function is just sort of exotic, and I'm about to show you. I've never seen anybody actually use this function in the wild. But if they did, I wonder what its derivative would be.
wait, so you use x to the x times whatever.
You don't want to see that.
I wonder what its derivative would be. Well, okay. Notice that I have a variable exponent, and that suggests that it might be profitable to do what? Take the ln of both sides. That's exactly it. Here's my verb for this, if I logify both sides, if I logify both sides, then I can demote my variable exponent to a multiplication. So let's do that. Ryan, you got it?
You got ln y. Sine x, ln x.
Okay. Now here he did something that's a little risky as you're getting used to this. He did two steps at once. Does everybody see what he did? He took the log of the right side and he used the log property at the same time. He did it right. He slipped. But if you find yourself tripping over yourself, go back and break that up into two individual steps. All right? So, he's got a decomposed log, and now, where from here, Ryan?
Take the
Good. And when I take the derivative with respect to x of ln y, what do I get every time? Yep, and I'm going to spell that as y prime here. Good. What happens when I take the derivative of the right-hand side? Davon, you got this?
You get, how would you get ln x, times cosine x plus sine x, it's 1 over x, plus sine over x.
Perfect. Good job. That's exactly it. And finally, we just need y prime by itself. So y prime would be equal to, somebody jump in.
So ln x cosine x plus sine x over x divided by
How'd you get divided by 1 over y?
So don't you take the y over?
Okay. Here is where I will say the word, the folly of talking about moving stuff comes into play. Notice what he wanted to do. Everybody observe this. He wanted to take the y over, and so he took it over.
No, divided by that.
Ah, what's
Yeah.
a simpler way to do what he wants to do? Multiply by y. Yeah. Simpler way to think about that is to multiply by y. So he was actually thinking about it in terms of correct math, and I was misunderstanding what he was saying. Okay, good. Good. And finally, how do I write this only in terms of y? Excuse me, only in terms of x? Replace y. What is y? It's what I said it was up there, x to the sine x. Is this an ugly result? Yes. Was it an ugly function to begin with? Yes. Are we surprised? No. How are we doing? Questions? Comments? Logs, as it turns out, have another trick up their sleeves. Here we use logarithmic differentiation to deal with variable exponents. But we can also use logarithmic differentiation to deal with very complicated products and quotients. Consider. Consider this problem, which strikes terror into the heart of students everywhere. Because as you look at y and you consider taking its derivative, your first thought is, I've got to do quotient rule. And then for d high, I've got to do product rule. For the whole thing, I've got to do power rule and chain rule and But the smart student comes along and says, you know what? I can logify both sides and make my life a whole lot easier. Let's do that. If I simply take the natural log of both sides, now I can do a logarithmic decomposition on this side right here. And let's see here. I could rewrite that as ln of the top minus ln of the bottom. And I've got a nice product sitting right there, so I can rewrite that as ln of the first plus the ln of the second. And then I've got three nice juicy powers sitting right in front of me, so I can rewrite those as power times the log each. And I've got the whole thing decomposed. Everybody with me so far? So you know calculus yet, just doing log properties. I also want you to observe how in your mind you can take and put the whole thing back to its original checker. Can you visually see that I'm going to get x cubed times x minus 1 to the 4th divided by x plus 2 squared when I put it all back? Mm-hmm. If you can see it expanding and contracting like that, you've got the spirit of the log properties.
It's like accordion.
Yeah, it is. Now that I have all of this, which is still equal to ln y, I'm ready for a derivative, and the virtue of my logarithmic decomposition comes into play. On the left-hand side, 1 over y times y prime. On the right-hand side, I can now go term at a time, and I get 3 times 1 over x, plus 4 times 1 over x minus 1, times the derivative of the inside, which is 1, minus 2 times 1 over x plus 2 times the derivative of the inside, which is 1 again. That wasn't hard. And therefore, y prime is equal to y times all that. Sometimes when I have to do the all that, I just put dot, dot, dot. And then I'm going to put y back where it came from. Times all this. Am I going to simplify this?
No.
No. Mr. King, where do you why do you use the chain rule?
Well, because chain rule is always on. So the derivative of natural log of x minus 1 should be 1 over x minus 1 times the derivative of
Oh,
x minus
okay.
1. Good.
Well, for like.
Does this make sense? As a method? Well, let me give you a roadmap for the next next little bit. On Monday, we're gonna do some review. We're gonna review the derivative rules that we've done so far. On Tuesday, I'm gonna give you a test. See that you guys
Test?
all of them. Oh, exactly it.
Just on this week, just by this week?
So the test is going to cover everything from the last test, roughly. But there's no way to escape all of the previous derivative rules that we had, right? I mean, power rule was technically on the last test, but it hasn't gone anywhere. Right? Quotient rule was on the last test, but it hasn't gone anywhere. So what we're looking at is trig functions, inverse trig functions, exponentials, logs. It's gonna be fun.
Oh, wait, wait, wait.
Yes, sir.